Welcome back to Biology 1440. Today we're looking at an introduction to chemistry. And this starts with the Big Bang. Chemistry begins when there was a singularity. 13 point some odd billion years ago, there's a singularity, a single point of matter that detonates, giving rise to the universe we have now. What was before the Big Bang? There's no way for us to know. It's impossible for us to see beyond that point. But matter is anything that has mass, essentially. And when we look at the basic units of matter, we have elements, which are what our atoms are. Like there's an atom of gold, right? It's an atom of gold, and it cannot be broken down into any other element through any chemical means. So it's the basic unit of mass, if you will. So the essential elements, those that are essential for life, are shown here. I would like you to be familiar with the 96% of the elements found in life. That's oxygen, carbon, hydrogen, and nitrogen. So those are those responsible for biology for the most part. Of course, other elements are important as well, like phosphorus and things. You can't have ATP without phosphorus, right? They're important, but they're not as abundant in life as those essential elements. There are also some trace elements found in life, like iron and iodine and things, but we're going to focus on those essential elements. Now, so like I mentioned earlier, an element cannot be broken down into any other element by normal chemical means. So things like oxygen, carbon, those are elements. Now, if you stick a couple of elements together, like you take an oxygen and you put a hydrogen on it here and you put one on it here, now you have a molecule. And a molecule is more than one atom joined together. Okay, so if you take sodium and you mix it with chlorine, you get sodium chloride. Now some molecules are the same atom. So you can have O2, which is two oxygens stuck together, right? That's also a molecule. So this molecule here, let me draw a circle around these two. So we have molecular oxygen, or O2 here. You can also have something like this, which is water, H2O, and it's a molecule and it's a compound. A compound is a molecule composed of more than one element. Okay? So these are the basic building blocks of matter, the stuff that makes us. And I bet a lot of you are familiar with the periodic table of elements. A lot of information on there. But if we look at just one of these, here we have potassium separated out so we can see all the things going on here. This is the symbol for the element. We have the atomic mass listed here, as well as the atomic number listed there. The atomic mass and number are pretty important parts that you should be familiar with. Not that you have to memorize it, I just mean know what they mean, right? You got to know what those mean. Now, let's look at atoms. So, elements are composed of atoms. Atoms are these tiny little units of matter that are composed of subatomic particles. Those subatomic particles, let me go back, include protons, which have a positive charge, neutrons, which have no charge, and electrons that have a negative charge. Okay, so the nucleus of the atom is composed of protons and neutrons. Not to be confused with the nucleus of a cell, different thing, but they're composed of protons and neutrons here. And then the electrons are in an orbital or various orbitals around the nucleus. They form an electron cloud, but we often draw them as if they're orbiting like a planet around a star. That's not quite accurate, but they're darting around in a cloud essentially around that nucleus. Now, one thing I want to point out is that let me show you something real quick. The way you can determine how many subatomic particles there are in an atom, the atomic number, this number right here, like for potassium, is 19. Let's do a smaller one to make it easier. Let's do our good friend carbon. It has an atomic number of 6. and an atomic mass of about 12, right? So that lets you know that in the nucleus of that carbon, there are 6 protons. So the atomic number lets you know how many protons there are. So there would be 6 protons in carbon. And to figure out how many neutrons there would be in that nucleus, you would look at this atomic mass here. So the atomic number lets you know how many protons. Atomic mass lets you know the combined total number of protons and neutrons. So you find the difference between the atomic mass and the atomic number there. They call this the relative atomic mass, right? It's usually a decimal, so just round. So that would be 12 minus 6, so that would be 6 neutrons in this case. And if you know the number of protons, you know the number of electrons as well in your typical atom of this element. So for example, if you had six positive parts in here, you have 6 protons in here, you're going to have 6 electrons out here. So positives and negatives cancel each other out. They're an equal quantity. All right, so the Octet Rule states that that the outer energy level, so when we have the nucleus, let's say of carbon, we have what we draw here, these energy levels, right? These are the areas where the electrons are. The outer energy level is usually in most atoms full when it has 8 electrons in it. So for the case of carbon, the first energy level in all of these things can hold 2 instead of 8. So the first one can hold 2, and then the outer one could hold a total of 8, but we know carbon has 6 electrons, so it will actually only have 4 out here because we have 2 here and 4 out here. Total number then adds up to 6. So it's not full. If this outer shell is not full, we know that this atom could react with another atom. If the outer level is full, like we see here in argon, for example, where it's totally full, that's a noble gas, it's not reactive. So if you have 8 electrons in that outer energy level, that atom will not be very chemically reactive. Helium also is not very reactive. It only has 1 energy level, but that first energy level, that first ring of electrons can only hold 2. So that's the one case where it's full with 2. So once again, atomic mass and number, I introduced this earlier. Atomic number is shown there. That's the number of protons. We have the symbol for the element, and then we have the atomic mass. And the atomic mass lets you estimate the number of neutrons by finding the difference between the atomic number and the atomic mass. And then you also know the number of electrons by knowing the atomic number. Now, the most common element in the known universe is hydrogen. It's super simple. It has 1 proton and 1 electron, and that's it, right? That's all it has. This is why later on, or if you've already learned about this in class, if you remove an electron from hydrogen and you have a hydrogen ion, it's just a proton. That's all that's left. So when we talk about proton pumps in this course, we're talking about a pump that pumps a hydrogen ion, which is just a proton with no electron on it. It's the most common element in the universe, and it shows up shortly after the Big Bang. About 300 million years after the Big Bang is when hydrogen really started to become common. Other elements, like helium and all the other elements, are formed typically in stars. So I'm not going to explain this whole thing to you. You can take a physics course or an advanced chem for this. But in the core of a star where there's a lot of gravity, we can take several hydrogens, and then under the massive weight of gravity, they interact with each other, and subatomic particles are created, and we form things like helium. And then if you have a really dense star, helium can get squished together in the dense core of that star and form other elements. So if we look at an example of this, in stars like our sun, we get a lot of hydrogen and helium, maybe a few other things, but hydrogen and helium is the really common stuff, right? But we can form carbon inside of stars, neon, oxygen, so on and so forth. And this star has iron at its core. iron is the heaviest thing you can make in the core of a star. And basically all of these elements came from stars. So if you think about it, we looked at those essential elements, here's carbon and helium. I'm sorry, carbon and hydrogen, for example, and oxygen. These are all super important for life. They all came from the cores of stars. So this is what physicists mean when they say we are made of star stuff. We are composed of stuff forged in stars. And we can actually observe this happening. It's not theory, it's observed to have occurred. So anything with a nucleus that's denser or bigger than iron can't be made in the core of a star, but actually requires a supernova to produce, a star detonating. So think about how cool that is when you look at the periodic table of elements. When we look at the Big Bang, which took place, like I said, 13.8 or so billion years ago, the singularity, it produced around 300 to 400 million years ago the first atoms. And then stars formed, and then they started making more elements. And this area right here, when hydrogen was the most abundant, well, when it was about the only element in the universe, that's as far back as we can observe with telescopes. As we look further out into space, we look further back in time, and we can see to about 300,000 years after the Big Bang. We cannot see this far back. I just think that's really cool that we can even see that far back. So after that, stars are born, detonate, making various elements that eventually combine to form our planet and eventually give rise to life, and then gave rise to me talking to you on this video. All right, we're going to pick up there in the next video.